In this third video, we're going to move away from examples a bit, and we're going to abstract to just studying properties that have to be satisfied by every ring homomorphism, no matter what the initial ring R is or the terminal ring S is. And the first thing that I want to point out is that all properties, we've covered this idea, and I really want to stress it. Rings are groups, and ring homomorphisms are group homomorphisms. And it follows that all properties that are satisfied by group homomorphisms are automatically satisfied by ring homomorphisms. So there's a huge list in Chapter 10 of Gallian of the properties that are satisfied by just an arbitrary group homomorphism. And I think it would be a good idea to go back to Chapter 10 and refresh your memory on the properties that are satisfied by group homomorphisms. I think in general, if you find that the idea of factor groups or group homomorphisms is something that's fuzzy for you, that you should go back and look at those chapters of Gallian or look at your notes from Abstract 1. Now, the second property that's satisfied is that multiplication and exponentiation are generally respected by the map phi. I say that out loud. That's what I mean when I take a look at these statements. Phi of n times r is equal to n times phi of r, and phi of r to the n is phi of r raised to the nth power. Remember that exponentiation, r to the n, means r is multiplied by itself n times r times r times r times r. So really this is just a generalization of the fact that phi of a times b must be phi of a times phi of b. You can generalize that to phi of any number of elements multiplied together is just phi of the product of that number of elements multiplied together. The first property, this phi of n times r, the n is a shorthand. The n is a shorthand for the unity element added to itself n times. And so for the first property, this phi of n times r equal to n phi of r, in order for that to be true, this must be, we must be talking about a ring, two different rings that have a unity element here in order for this first property to be satisfied. Now the third property I want to cover here is that if I is an ideal of R, and then we look at the homomorphic image of I under the map phi, so we look at phi of I, the alternate notation I was using earlier on in the presentation is Im of I, the image of I. You can also denote that by phi of I. And this happens to be an ideal, not necessarily of the whole ring S, but this happens to be an ideal of the ring that we map to, which is the image of R, or phi of R. The next property that I want to cover about ring homomorphisms is almost a converse to the previous property. Let's suppose that I start in the ring S, and I'm looking at J, and this happens to be an ideal of S. What I could do is I could look at what's called the pre-image of the ideal J. This is equal to the set of ring elements in R that map somewhere inside of J. So it doesn't need to be surjective. We don't need to hit all of J. We just need to map to some particular element that belongs to J. And this set that we have written down right here happens to be an ideal of the ring R, this pre-image of the ideal J. So the third property, in a way, just to kind of summarize a bit, is that if you start with an ideal and then you map it, you get an ideal. The fourth property is if you start with an ideal in the image and you look at what mapped to it, then you're also getting an ideal. You can kind of combine these two things together and say ideals map from ideals, ideals come from ideals, etc. So the fifth property is if R has a unity that we're going to denote by 1, and if it happens to be the case that the ring S is not just the ring which is the number 0, then when we look at the image of 1, this is also the unity of the image of phi. So back in group homomorphisms, where we only had one identity, one of the group homomorphism properties was that phi of the identity is the identity of the image of where you're mapping to. The same thing is true about the unity. If you switch from the additive identity to the multiplicative identity, or if you switch from the additive identity to the unity of a ring, then what you get, this phi of 1, is the unity of the image. And last but not least, this is a new property that is really helpful for ring homomorphisms, and I'm going to try and give at least one example of how to use this property later on in the slides. But a lot of times we are interested in knowing if what we have is a ring isomorphism. So not just a ring homomorphism, but a ring isomorphism, meaning that in addition to this homomorphism map being a ring homomorphism, it also happens to be one-to-one and onto. So if we want to check for that, one way that we can know that we have an isomorphism between a ring R and its image of phi, this will happen if and only if the kernel of phi is just the additive identity of R, just the set containing this number 0. This is really helpful to us when we're dealing with ring homomorphisms because many rings, or most of the most interesting rings to us, are going to be infinite, and so we're not going to be able to just look at the size of the kernel of a particular map like we often could, at least in my abstract algebra class in the first semester. I did a lot with group homomorphisms between finite groups, and most often the interesting examples of rings are infinite. And so the methods that we've had before for checking that a map is one-to-one may not always work. So here you have a couple different options. If you want to check that a map between R and its image is a one-to-one map, you could check using the definition of one-to-one, but you could also check that the kernel of this map is just the additive identity. So this gives you another tool for proving that you have a one-to-one map when you're talking about ring homomorphisms. Now, another thing I want to discuss in this video is kind of hitting on that last fact, that last property of ring homomorphisms. And this is the kernels of ring homomorphisms are very important. Now, the theorem is here. Suppose that phi is a map from R to S, and that this map happens to be a ring homomorphism. Then the kernel of phi happens to be an ideal of R. So let's do the proof right here, but let's talk through a few things. Again, remember that ring homomorphisms are group homomorphisms. So we already know that when we have a group homomorphism from a group R to a group S, then the kernel of that map is a subgroup, a normal subgroup of the original ring R. So here, what we want to do in order to show that the kernel of phi is an ideal of R is we want to use that ideal test that we discussed in a previous video. So we're going to check that three things hold about the kernel of phi. We're going to check that it's a non-empty, that it's closed under subtraction, and that it's closed under multiplication from an arbitrary element of the ring R, not just amongst itself, but closed by multiplication by an arbitrary element of the ideal R. And my claim in saying that this is a group homomorphism is that we don't have to check those first two criteria. We don't need to check that the kernel of phi is non-empty, and we don't need to check that it's closed under subtraction, because those things are automatic from the fact that the kernel of phi is a subgroup of the ring R. So I'm cheating a little bit, and I'm saying two of the three properties we need to check automatically hold because ring homomorphisms are group homomorphisms. So if you're unfamiliar with the proof that the kernel of phi is a subgroup, a normal subgroup of R, then you should go back and review that. Now, what I will show here is that we want to show that the kernel of phi is an ideal. So what we need to show is that if I start with an arbitrary element A, just in the ring R, and then I start with an element little r that belongs to the kernel of phi, that when I multiply those two things together, and I look at AR, that it belongs to the kernel of phi. That is, what it means to belong to the kernel of phi is it means that you map to 0 under phi. So what we want to show is that if we pick A and R in this manner, that phi of the element A times R is equal to 0. To do this, we're going to use the fact that we have a ring homomorphism here. We want to show that phi of A times R is equal to 0, so let's start with phi of A times R, and let's rewrite it as phi of A times phi of R, which we're at liberty to do, because phi is a ring homomorphism. So we know that that multiplication can be done after we map into the ring S. So phi of A times R is phi of A times phi of R. And because R belongs to the kernel of phi, we know that phi of R is 0. That's how an element gets admitted into the set the kernel of phi. When we take phi of it, we're getting the additive identity of S. So when we're looking at this phi of A times phi of R, what we have is phi of A times 0, since phi of R is 0. And 0 times anything is equal to 0. So when we put this all together using the transitivity of equality, what we have is that phi of AR is equal to phi of A times phi of R, which is 0 times phi of A, which is 0, and altogether phi of A times R is equal to 0.